Is on. I'm not muted. And I think one of our other lectures, the audio was not there. Was that our class? I don't know. One of the lectures. I posted online, but there's no audio. All right, everyone. Well, mini exam 5 is due today, if you've done it. All right. I had a feeling I'd be getting all these mini exams at the end of the semester. Okay. All right. Yeah, these are kind of, because I'm having to cram them all in now at the end. They're shorter. Yeah, I know, but the people who did them in the beginning are like, man, this isn't fair. Yeah, I know. I think there's 4 on this one. Did I print enough? You have to remember, I think I might have an extra one here. I don't know how many people are here today, but you know, the main idea here behind these mini exams is just to make you think. It's all about just trying to get you to think about these things deeper than where the book might take you. The problems that I'm presenting you with on this mini exam I just handed out and the one you just handed to me, those are a little more along the book level of problems. So I do have a little bit of a hint on, do you have your exam? Where the heck did I just put those? Did I put them in there already? Here. No. The one that you just did? Yeah, this one. You turned yours in, right? Where did I put them? Oh no, I put them in my backpack. Okay, there we go. Anyone else turning in today? No? That's it? Yes? I do have a hint on the exam that I just gave you. And that is on number 2, I believe it's asking for the mass of a wire or something like that.
Oh, this one.
Yeah, yeah, that one. Yeah. Yeah, you're going to have to go staple that. I don't think I have a stapler here. English lab right across the way. Are there any extras? Let me see.
Well, here's one here.
Yeah, take that one for now. So on number 2, is it asking for the mass of a wire or something like that, or center? Center of mass of a wire. So I never did that. I never actually covered that. I did do centers of masses of laminas, 2-dimensional objects, but I never did the center of mass of basically a curve, right? I never did that, but it's in here, okay? So you're going to need to do a little research to find the formula, all right? It's in a section we've covered already, so. All right, let's get moving here. We ended class last time, and we did not quite finish this problem with the person who was climbing up along the silo tower. Remember that? And we had set up most of it. We had said that the force, the vector field, which really represented gravity, was a pretty simple vector function, 0, 0, negative 200, right? And that just represented the force of gravity straight down. And we got the 200 from the fact that it's a 180-pound man carrying a 20-pound tool bag, right? And then what we need to do is we need to come up with a vector function which represented his path up the silo. And we had started developing that, R of t, and we had said that was, thank you. We had said that was 20 sine t, 20 cosine t, 20 sine t, thank you. I need to get you a copy of the next exam. I didn't print out enough for some reason, okay?
I can print it out through the files.
Yeah, I don't think I have it up there though. cosine t, sine t. There we go. So remember this? This basically wrapped us around, but we needed to move up, and that's where we left off. And I said, why don't you go and try and figure that out? So did anyone figure out what this last component needed to be? We needed to rise up by 90 feet.
Would this be 90?
90 would mean, if you just put 90 there, that's just going to keep us at 90 the whole time. We're wrapping ourselves up the silo. We're going up.
So for every pi, you'd go up 20, right?
For every
with the first
pi.
two components? Or you'd go up,
What might help us here is to, when we read the problem, it says it takes 3 revolutions to reach the top, right? Mm-hmm. So using these two component functions, what would my restriction on t have to be in order to make me go around 3 times?
0 to 6 pi.
0 to, what's that? 6 pi?
6 pi, yeah.
Right? 0 to 6 pi should make me go around 3 times completely, right? So my t being 0, I'm going to start at the bottom. 6 pi is going to wrap me around 3 times, but I need to be moving up while I do that. So I need that at 0, I'm on the ground, 0, and I need that when I'm at 6 pi, I'm up at 90, right? So no one came up with it?
90 t over 6 pi.
90, yes, exactly, good. 90, I'm going to do 90 over 6 pi times t. So just think about that expression for a moment, right? This is, when t is 0, this is 0. And when t is 6 pi, the 6 pi's cancel and you're up at 90. And so all t's in between should take you up. And it's linear, right? So another way to visualize this is if you were to take that path that's around the silo, right? And kind of imagine, like, I don't know, like unwrapping it. You've got to go up 90 feet, right? And you got to do this in 6 pi, right? Like time-wise. So it's kind of like what's the slope, right? That would take you other way. Sorry, right? What's the slope of that? It's kind of like we're taking that and wrapping it around. So the slope of this line would be rise over run. So 90 over 6 pi. Make sense? Okay. And that's it. Now, the rest of the problem is just computing the work, right? So to do the work, and I don't know if I'm going to compute the whole thing, but to calculate the work, we learned last class that work is the integral over the curve C of f dot dr, right? That was the big formula from last class. And so f for us is given, right? And we should also, let me write the other version of this. This becomes a to b. This is f evaluated at the curve, and then dotted with dr, which really for us is just r prime of t dt. So that's the formula. That's that formula written out a little bit in a little more detail. So our f, our field, we don't have to evaluate it at the curve because our field is constant, right? They're constant components.
Yep.
So this becomes integral 0 to 6 pi. That's our restriction on t. And then we have the vector 0, 0, negative 200. And then we're going to dot that with the derivative of that. So the derivative of that is negative 20 sine t, 20 cosine t, and then finally just 90 over 6 pi without the t, right? Because we took the derivative. And then dt. And what's the really nice thing here when we dot these?
The x and the y components.
Yeah, the x and the y components are gone because this is 0, 0. So when you dot, you get nothing from those. So the only thing that contributes to the integral is going to be the last two components multiplied. So it's negative 200 times this, right? So what is that? Arithmetic, I tell you. Negative 200. So negative, what is that, 18,000 over 6? Pi? Missing something. That's it. dt. And then we could integrate this. This is all just constant, right?
Yeah.
That could all just come out. And we're taking the antiderivative of 1 with respect to t, which is just t. So we get here at the end, negative 1800 or 18,000 over 6 pi. Here's t. We're going to evaluate that at 0 and 6 pi. So when we plug in 6 pi, the 6 pi's cancel. And you just get negative 1800 or 18,000. Keep on saying 1800. 18,000. And then when you plug in 0, you get 0. So negative 18,000. Right? That seems right. I don't think I made any mistakes here. Negative 18,000 what? So I put here, because the man's weight was measured in pounds and everything else was measured in feet, it's going to be, the unit we're going to have here is foot-pounds. Right. And it's a negative number. And the reason why is because our path, if you look at the field, right? The field was a bunch of vectors pointing straight down. And our path went against that field. We had to go up against that field. So we consider that when they're opposing directions, you're going to get negative work. When they're, like if he was going down, it would be considered positive work. So it's just the way it works out. We have to orient it one way or the other, right? One of them has to be positive, one of them has to be negative. It's kind of like if I throw a ball at somebody, that ball is either moving away from me like a positive speed, or if you're the other perspective, it's closing in, so is it positive or negative to you? It's all kind of relative, right? So we have to pick up or down. Negative work is against the field. Questions? I'm gonna change the problem. Just slightly tweak it. Okay, I'm gonna leave the same exact setup up here, but I'm gonna make this guy have a little bit of an issue. All right? He's carrying this can of paint up, this silo, and he's not paint. He's gonna carry 20 paint pail. He's supposed to go up to the top and paint something, all right? Bucket, he's got this bucket of paint, all right? He's walking up there. He's gonna go around the silo. So that right there won't change the answer at all, right? But here's the catch. Paint is leaking out at a constant rate of, let me see, I worked this on my own because I wanted to not have to do some of the computations. So let me stick with the same thing that I chose to do. 0.2 pounds a minute. All right? And there's another thing I want to add to this, that I need to add to this. It takes him 6 minutes to climb to the top. So a little more information about this now, right? He's got this bucket of paint. He weighs 180 pounds. He's carrying a 20-pound bucket of paint. But as soon as he starts walking up this silo, which takes him 6 minutes to do, as he's walking, he doesn't notice that 0.2 pounds of paint are kind of trickling out of this thing every minute, all right? So the work should be different, right? Because his weight is decreasing as he's going up now, right? So is his R of t any different?
No. Yeah.
No and yes. It depends on a few things. Let's start with the force first. Let's do that. I think that might be the easiest. What about his force vector? We still 0, 0, right?
Yeah.
Okay. So how does that z component change now?
It's going to be 200, but it's going to be
minus 0.2.
We're going to go negative 200 for the vector down,
Yeah, negative
okay?
200
So
plus
plus, okay, so plus now what though?
0.2.
0.2 pounds, so I'll put 0.2 pounds
So D.
every minute, right? So we need to multiply this by t. So now t is actually what's the word I'm looking for? We are now establishing what t is at this point, okay? T is a measurement of how many minutes there are, right? 0.2 pounds every minute. So from this, can we establish what the restrictions on t are going to be for this problem? 0 to 6, right? No longer 0 to 6 pi like the previous problem, right? It's going to be t is from 0 to 6 because it takes them 6 minutes. Okay? Now, r of t. Does anyone have any questions on this part? Why it's negative and positive or anything? Negative, vector is down, but the vector is going to get shorter, not as long, because he's going to start weighing less. So to weigh less means we need to add a number to this to make it a smaller negative number. Okay. All right, r of t. Do the first two components even matter? They don't, do they, right? But I'll still write them. 20 cosine t, 20 sine t. And then now again, we need to go and be able to be at 90 at the end and 0 at the beginning, right? So t is, what's going to be the z component here? 90 over this time 6t, right? Not 6 pi. So if we start at 0, we'll be down at the ground. When we get to t is 6, that's 6 minutes later, we will be at the top. But what's wrong? What's wrong with that? It's not right. These are not going to draw 3 complete revolutions anymore. You see? It's like we're trying to get t to work in here. So we say, okay, t is number of minutes. This should get us up to the top, but now we're not drawing 3 complete revolutions.
Before we were doing 0 to 6 pi. So now since we're going 0 to 6, we should put pi in front of t.
Exactly. We have to figure out a way to make these still go from 0 to 6 pi. So what we'll do is we'll tweak these, and this will now be 20 cosine of pi t, or t times pi. This will be 20 sine of pi t. Does that make sense? That way when you start at 0, you still... Yeah, let's put it in here. You'll see.
Because if we just leave the t when we're saying the restrictions are from 0 to 6, then we're never going to get to 6 pi, which is 3 revolutions.
Yeah, you won't get the full revolutions. Yeah. You'll go all the way to the top, but you won't go all the way around, which means you're not doing what this says you're doing. It's supposed to be this nice uniform, right? It's almost like you stretched it out,
Yeah.
but you're not doing 3 full revolutions.
Because before, I guess we're basing it off just the revolutions, but now we're basing the revolutions off the time.
Off the time, exactly. So before, we didn't have a time element in it, did we? That in the previous problem, he could have been just going real slow, right? And get to the top. 6, what am I doing? Pi t. He could have been going really slow, right? And it could have taken him 3 hours to get to the top. Or he could have ran up and it taken him 3 minutes. The work done is the same. All right? Time does not matter. Time here matters because his weight is a function of time, right? So therefore, we have to incorporate that into the entire problem. I thought I saw a hand. Question, comment.
I had a hand up when you wrote 6.
When I wrote 6, yeah, I would have too. Thank you for... Okay, good. All right, so we good? Does everyone agree that that's going to wrap us around and move us up?
No pi on the t?
Not here. Not here. Because t is going to go from 0 to 6, right? So if I go 0 here, I'm at 0. If I go to 6, I'm at 90. Yes?
Sorry if I'm making you repeat yourself. So by writing it this way, you're basically like, you're assuming that the change in distance is constant, like each
Yes.
not like depending.
We are saying that this is, did I say a helical? Yeah, helical staircase. So the helical part of this word problem kind of is assuming that this is a uniform staircase going up at the same rate the whole time. So it's not like it has a steep section, then a flattened section, then steeper. It's like we're taking this. Take a triangle like this, okay? Take that and wrap it around a cylinder.
Oh, no, what I meant was like you're not assuming like he's gonna go faster after like some of the paint falls out. Like he's always gonna be going at the same speed.
Well, he's going to take 6 minutes to get to the top.
So it doesn't really matter.
Yeah.
Okay.
Yeah, that doesn't matter because if he slows down the beginning, right? He's going to lose more, but then he's got to speed up, right?
Still gonna take him 6
Yeah.
minutes.
Well, you know what? No, I think we've got to be uniform here.
Yeah.
Yeah, because if he just lets the whole bucket empty out in the very beginning, then he's going to weigh almost like just barely 180 pounds and then go the rest of the way up. So yes, it has to be uniform. He's walking at a constant rate.
Okay.
Yes. Even though he's lighter, he's still, we could incorporate that into it also, but that would make it a much more difficult problem if his speed was also a function of the time or a function of his own weight. Now that starts to get pretty complicated.
Because the weight's a function of time, then the speed's a function of weight.
Yeah, then you might get circular. So you might have to define the speed function just explicitly. Yeah. See, this is what makes the real world so hard, though. You start out with examples where you have very tight constraints on the way things are happening. But once you get to the real world, so many things become variable, so many things become dependent on other things. It gets complicated, right? All right, so now let's do this. The work is going to be the integral over this FDR, which for us is going to be now 0 to 6. Okay, the F we have, let's go ahead and dot them. Let's get the derivative of this here. Negative 20 pi cosine sine pi t. And then positive 20 pi cosine pi t. Everyone's okay with that pi out there? And then the last one is just 90 over 6.
You didn't have to do that though, don't you?
Yeah, we don't, because when we dot it, we're only going to get the last component anyway, right? Yes? But, it is what it is. So we go, this is separate. Okay, so this is F dotted, so this dotted with this just gives us negative 200 plus 0.2 t times 90 over 6 dt. And then from there we could distribute through, and that's a pretty simple integration also, right? All right, I'm not going to finish that, but that's the integral for it. So this is why they say, I hope it's obvious to you that this is why they say in physics that when it comes to like work done against gravity, your horizontal displacement matters. I mean, it doesn't matter at all, right? This left and right movement is no work. The only thing that contributes to the work is this up and down motion. And that's because the force vector has zeros as these two components, right? Now this is a simplified version of gravity because we're saying it's straight down, not straight to the center of the Earth, which is something maybe a little different because the Earth's not perfectly spherical. So I mean, again, you can get more complicated, can't you? Yeah. All right.
If your T's weren't, this is just kind of theoretical, but if your T's weren't constrained, wouldn't you get to a certain point in T where that number is going to reach 0? Like, for example.
Oh yeah, where you're gonna.
Say like basically when the paint just runs out completely.
Yeah.
If your T is like 2,000.
Yeah.
Something like that.
Yeah, we would at least have to put a constraint like, well, 20 pounds, right? 20 pounds, so T is what, 100? T could only go to 100, right?
But then you'd say that it leaks out at a different rate because the weight of the paint is...
Oh, you're saying like the rate that it comes out is changing because...
Oh, no.
Yeah, okay, yeah. Yeah, the bucket has some sort of, yeah, see. Yeah, well, that's why, in college algebra, that's why you start off like a falling object on Earth. They give you a quadratic function. They say, oh, take the air out, right? And this is what it is. And that's truly, it's that simple. It's a quadratic function so long as there's not air. You put air in there, it's no longer a quadratic function, right? And then you start throwing other things in there, like, okay, it's rotating and it's a tennis ball. So what do all those little furry things on the outside of a tennis ball do to turbulence and, right? Yeah. We do our best to model the real world with mathematics. We do the best we can, right? But it's not perfect. There's always some error in there. All right, this is an interesting example. This is our last example. A 10 kilogram object moves with a position function given. So we've got this thing, this object. You all right?
No, yes.
Oh,
Sorry.
okay. No. Thought you were fanning yourself off like, and you reacted like he smelled real bad or something. Okay. All right, so we have a 10 kilogram object that's moving with a position function given. So this 10 kilogram object is moving in three-dimensional space, and we're only looking at it between t equals 0 and 1. So it's only moving for, let's say, 1 second or 1 hour or 1 minute or 1 day or 1 year, whatever it is. We don't have a real measurement on time t here, do we? We don't know the unit for time. We also don't know the units we're using for this r. We don't know if this is miles or feet or anything else. And the last problem with the silo, we had that, right? We had feet, pounds, right? So we want to find the work done on the object during this time period. Okay, so work we know is integral over the curve f dr. Does anyone see a problem here? Like an issue? Where's f? Right? Where's f? Where is f? F is not given to us, is it? Now, nowhere in this problem am I saying that this object is moving on Earth. Okay? So there's nothing here that says that this 10 kilogram object is under the influence of gravity. The previous example, man walking silo, I think we could all assume that he was under the force of gravity. But nothing is saying we're under the force of gravity. In fact, we can assume that there is no gravity. So this is an object moving in space, let's say. So there's no gravitational force on it. Okay? So what is force then? Like, how are we going to get F? Well, do you agree with this? Well, you've seen this, haven't you? You've seen that or no? Isaac Newton? Force equals mass times acceleration, right? Force equals mass times acceleration. We have a mass, right? 10 kilograms is not a weight, it's a mass. So we're given a mass. Do we know an acceleration? Do we know the acceleration of this object?
Solve it because we have a position function.
We have a position function. And the first derivative of a position function is the velocity function, and the second derivative is the acceleration function. Yes, and there are functions of time. So watch. This force equals mass times acceleration. I'm about to change it into something that we can work with. Our force, the force being applied on this object, is a function of time, which basically means where it is. And that will be the mass of the object times the acceleration of the object at that particular point in time. So do you all see that that is F equals ma? Right? So if you have an object moving in space without gravity there, then the only force acting on it is its own mass times its own acceleration. So for us, this is 10 times. Now we need the acceleration function as a vector function. So we're going to have to take the derivative twice. So what is r prime of t? So that's going to be... Isn't that kind of cool that you can get the force from this, just using that? Okay. So we take the derivative of it first. We get 4 cosine 4t And then we get 8 cosine 8t.
Why wouldn't it be
And then
4 sine
2t.
cosine t?
4
4 sine 4t times cosine 4t.
4t.
Is it
Are you trying to do like a product rule or something?
No, because I mean, the derivative of sine, so you do the derivative of the outside.
Yeah, okay, so the derivative of sine of 4t is cosine of 4t, right? Then you do derivative of 4t, which is 4. I think you're saying 4t or something? I don't know.
Wait, what the hell was I thinking?
I don't know. I don't know. Are we okay with that?
Yep.
Okay, now we go derivative again. This is velocity, this is acceleration. Velocity, acceleration, right? So second derivative through, we get negative 16 sine 4t. And then here we get negative 64 sine of 8t. And our last component is just 2. So this is our acceleration. So this is our acceleration function as a function of time. There it is. So now we come back over here, and we're going to multiply that by 10. Can we just do it all at one time here? This times 10 is going to be negative 160 sine of 4t, and then negative 640 sine of 8t, and then finally 20. So that is our field. That is our force field. It's like Star Wars-ish, right? This is our force field. And it is a function of time, isn't it? It is a function of time. And now let's go and do this right here. So I need to take my field and dot it with the derivative of my position, which is that one, right? Okay, so let me do that. So my work will be the integral from 0 to 1 of negative 160 sine 4t, negative 640 sine 8t, and then 20, dotted with 4 cosine 4t, 8 cosine 8t, and then 2t. And then all of that, integrate that with respect to t. So that dot product is not, it's not as nice as the previous example, right? Because you don't have all those zeros in there. So let me keep going. It actually turns out to work out pretty good. So integral 0 to 1, when I dot this, it's just this times this. Let me just write down this stuff so I don't make any mistakes, because I already did this. So you should get negative 640 sine 4t cosine 4t, and then minus 5,120 sine 8t cosine 8t, and then plus 40t. Okay, all of that dt. And then you go to integrate that, right? We clear on all that, where that all came from? Okay, now what I'm going to do, or what I did when I worked this out the other day, is I went ahead and used this double angle identity that says if we ever have sine of 2u, it's equal to 2 sine u cosine u. In other words, if we ever have sine of something times cosine of itself, the same thing here, I can just take that 2, divide both sides by 2. So this expression becomes half of sine of doubling the angle. So these two right here would become half of sine of what? 8t. And then these two right here would become half of sine of 16t. And it's just going to make it a little easier for me to integrate those. Yes?
Why wouldn't you leave it as sine of AT on the second part, so then you could factor it out?
I'm not sure what you mean.
like, leave the sine 8t. Oh, wait, you can't do that. Never mind. Never mind. Well,
I mean, you could.
now you can, right? With the 16t, you can do like 1/4 sine 8t. And then you can
1/4,
combine
wait,
sine
1/4
8t.
sine 8t, what?
He's just saying leave it as sine 8t so you can combine the two like terms.
Like, so the 1/2 sine
Oh,
16t. you can
oh, like
combine
leave this
sine
one then factor out a
Well,
sine?
no, I'm sorry. That's what I was saying at first, but then I realized it was wrong. But now, if you change the sine 16t and do the 1/2 thing against, then you have like 1/4.
Wait, change it how? How am I going to change sine of 16t?
I'm just going to leave that.
No, I mean, I'm willing to
No,
do
I-
anything as long as it's like, you know, legitimate, I'll do it. It's all good, Milton. All right, we're going to keep going. Negative 320 sine 8t. And then when I put those together, I take half of that, so minus 2560 sine 16t. And then this one didn't change, plus 40t. Milton, do you want me to do anything with the 40t? Change it to maybe like a pi t or something? I'm just messing with you, Milton. Come on. All right, can we integrate that? Yes. Okay, so when we integrate those term by term, the numbers in this work out really nice, actually. So remember, the antiderivative of sine of 8t would be negative cosine of 8t, but then you'd have to put a 1/8 in front. So when you do that, you should get 40 cosine 8t. So I'm doing the antiderivative here, plus 160 cosine of 16t, and then plus 20t squared. And we're going to evaluate that 0 and 1. So that's just the antiderivative of each of those. And then when you plug in, it actually is not that nice, because when you plug 1 in, you get cosine of 8, which is not something we know. So this turns out to be 40 cosine 8 plus 160 cosine of 16. And then when we plug 1 in here, we get plus 20. Then we're supposed to take all of that and subtract from it whatever we get when we plug in 0. And when we plug in 0, things are a little better, because cosine of 0 is 1, right? Cosine of 0 is 1, and then 0 here goes away. So we should just get 40 plus 160 here, right? Yeah, which will be 200, and then we'll subtract it from there. So it's going to be this, plus 20, take away 200, and that's your answer. Okay? Now, because we didn't have any units of measurement for feet or miles or anything like that, can't really give a good answer in terms of our work. Like, we can't really say Newton meters or foot pounds or anything like that, because we don't have any sort of distance measurement. Okay? So the moral of this problem is that even though we weren't given F, we can derive F using F equals ma. All right, let's move on. We are done with this section, and we're ready to move on to the next section, 13.3. And I'm going to just start us out with 13.3 by making you think about something. Do you agree with this? Oh my gosh, I can't. Milton? What are you doing? What are you doing to us? Okay, that's one of the versions of the fundamental theorem of calculus. That's the evaluation theorem. Right? So we all understand that? Okay. I'm going to write it in a different way. Do you agree with that? That's the same exact thing, isn't it? Because what we meant here is that capital F was the antiderivative of little f, right? In other words, little f was the derivative of capital F. So if I replace capital F with little f, then this in here has to change to the derivative of that. So this is the same formula, right? Okay. Just want to start with that. So this is something we recognize. 13.3 is titled The Fundamental Theorem of Line Integrals. That was the fundamental theorem of calculus, the evaluation theorem. We are looking now at the fundamental theorem of line integrals, which says, suppose you have C, which is a smooth curve. So that curve being smooth means there is a couple of things. We go back and look at it in our notes from chapter 10, but let's not worry too much about it right now. Let's just imagine it being smooth. So we have a smooth curve given by some vector function r of t, and we're defined between a and b for time, or t. And let's suppose that f is a differentiable function of 2 or 3 variables. In other words, f is a scalar function, so it's either like f of xy or f of xyz, but it's a scalar function. And suppose that we take the derivative of this function, which is the gradient, right? We take the gradient, then look at this result. Does that look familiar? Does it look kind of like what I just had on the board? We're saying the line integral over c. Okay, so that's like, for us, was like the integral from a to b. It was just same sort of idea. This is the derivative of f dot dr is equal to, what is little f without the gradient? That's kind of like the antiderivative in a way, right?
Yeah.
Evaluated here minus that scalar function evaluated here. R of b is the endpoint of the curve, and R of a is the endpoint, the starting point of the curve. So, in other words, like this. A, B, this is cal 2. This was our function f, right? The area of this, if you want to know the area of that, then all you have to do is calculate this, right? That was what was so great. If you want that area, you find the antiderivative of that and evaluate at the 2 endpoints. That's what we did. This is saying that if you're trying to find the work done, right? So remember, the gradient of a scalar function is a vector function, right? This is a vector function. So if you're trying to find the work done, integral over c of f dot dr, the work done by moving along this curve r, or c, we'll call it c. If you want to know the work done going through here, then all you have to do is evaluate the scalar function at the 2 endpoints and subtract. It's crazy, but that's the fundamental theorem of line integrals. Now, there's something very subtle, but it's important. This theorem does not work for any field. Like you can't just replace that with f in this theorem work. This thing right here must be the gradient of a scalar function for this theorem to work. And what did we say? If a vector field was the gradient of a scalar function, then what kind of field did we call that? Conservative, right? This is only going to work with conservative vector fields, this fundamental theorem of line integrals. So that's what it says here. This theorem says the line integral of a conservative vector field is simply the difference of the value of the function f at the endpoints, which means all the stuff that happens in the middle doesn't matter anymore. The path doesn't matter. All that matters is what's happening at the endpoints, which is kind of like here. We're trying to find the area under here. All that crap doesn't matter. All we need is the antiderivative at the 2 endpoints. That's all we need to figure out the area. Further, the line integral on any 2 paths that connect the same 2 points are always equal if f is a conservative vector, if f is conservative. So imagine we had this path C, we'll call it C1, and what if I did another path like that, and we call that C2? Then the answer will be the same, regardless of the path, so long as what? The field that we're in is conservative. So we talked about this last class. We said, Does path matter? And we said, yes, it does, right? We got different answers going, if went from one point to the other using one path, we got one answer. We did it another path and we got a different answer. This theorem is saying if the field you're moving in is conservative, then you get the same answer regardless of the path. So we get this thing called path independence. All right, let's just use the theorem once just to see how it works, and then we'll get further into the theory of this. So let's start with a scalar function. All right, let f of xy be x squared plus y squared, and c is this curve, and we're defined from 0 to pi. Find this, right? Find the work done by the gradient vector field. How do you want to do this? There's an easy way and a hard way.
Take the partial with respect to x and y first.
Okay, so go and compute the gradient first. Okay, and once I do that, what? Dot that with dr, which is the derivative of this. Dot the two together, right? And then go and integrate that from 0 to pi. Do you all understand that?
Yep.
That's the hard way. What is the fundamental theorem of line integrals telling us?
So
Yes.
F is conservative.
Yes. Is it conservative? Oh, I'll let you finish. If f is conservative.
Conservative, then the path does not matter, and we only need to evaluate f, the function f, at each given point.
That's right. So if the field we're integrating over, right here, if it's conservative, then we don't care about the path. We only care about that function evaluated at the endpoints of this curve. All right? Is it conservative? Well, look, isn't the gradient of little f like what is required in order to say a field is conservative? Right? That's when we define conservative, we said a field f is conservative if f happens to be the gradient of some scalar function. But I'm telling you to go integrate the gradient of a scalar function. So just by definition, this is always going to be conservative. All right? So on a take-home test that you might have, I might ask you to calculate this. And you might do it a very hard way, or you might do it a very easy way. The hard way, I think, is almost impossible. If not, it's very time-consuming. So we are going to use a fundamental theorem of line integrals right now. So using the fundamental theorem of line integrals, obviously, the gradient of f is conservative, right? Is conservative, right? That's by definition. Therefore, the line integral over c of the gradient of f dot dr should be equal to f, the scalar function evaluated at the end point of the curve, minus the scalar function evaluated at the beginning point of the curve. So all I really need to do right now is figure out what the 2 points are. So what is r of b? What is r of a? Let's figure those out, okay? So let's get that. What's r of b for us? Well, what's b? Pi, right? And what's a? 0. So r of b really means r of pi. And what is r of pi? So what happens if I plug pi into my position function? It's going to give me a vector, isn't it? What's the vector it gives me?
0 pi.
0, because sine of pi is 0, right? And then cosine of pi is -1, so negative pi here. Okay, so I plugged in pi here, got 0, that didn't matter. Plugged in pi here, got -1, but then times pi, right? So you get this vector 0 pi. Now let's also go get r of a. R of a for us is 0, so r of 0, well, that's an easy one, right? That's the 0, 0 vector. That's 0 into here. Okay? Plugging 0 in here, 0 in here. So now we have the two endpoints of my curve, right? What do we do with those two endpoints? We evaluate the scalar function at the vector function. This is that weird notation I showed you earlier. What does it mean to take this vector? Let's do this one. What does it mean to take that scalar function and plug in the vector 0, 0? What does that mean to us? Replace x with 0 and y with 0 into that.
Respective components.
Right? The respective components go into the x and y, respectively. And then we'll subtract from that f evaluated at, oh, I got those backwards. 0, negative pi. Oops. And then this one was 0, 0. With me? All right, so let's plug it in. If we plug in 0 for x and negative pi for y into that scalar function, we get a scalar answer, and that answer is what? Pi squared. Minus, and if we plug in 0 and 0, we get 0, which would be pi squared then. The work done is pi squared. Now, what do y'all think? That's pretty nice, right? I just want us to get an appreciation for what we did not have to do. Okay, it should have been my field, which would have been 2x. Well, let's do it up here. This is the hard way. I'm gonna set it up though. First, we have to we calculate the gradient of f, which would have been 2x, 2y. Agreed? And then what we would have done is we would have taken that here, dotted it with dr. Let me do the dot dr here. What's dr for us? Well, we got product rule here, right? So that would be sine t plus t cosine t, and then derivative of that, which would be cosine t, and then I believe it would be minus t sine t. So that's our dr. And then we have to do, hold on, the gradient of f, which is this, but evaluated at the curve. So all my x's get replaced with what?
T sine t.
T sine t. All my y's get replaced with t cosine t. So this would have been 2t sine t, 2t cosine t. And now I would have dotted those. Question?
Why were your bounds from 0 to 1?
I don't know, because I'm just not thinking.
Oh.
Whatever you drink, I drink. All right, dotting that. You see this? Do you see how bad this is going to be? I'll go one more step. 0 to pi. Thank you, Milton, for bringing that up. Dot this. So I've got to go here, dot it with this, right? So it distributes to both. So we've got 2t sine squared t plus 2t squared sine t cosine t, right? That's this, there, and there. And then I got this one to there and there. And then I got to start integrating all those, right? Do you really even want to bother? Or like, do you want to integrate that? That looks like integration by parts, maybe. Yeah, you first have to do the sine squared as a power reducing formula, and then, yeah. And then, yeah. Do you see how bad this could be? Pi squared. I like that better.
Could you use this method to solve some of these previous problems that we've done?
As long as they're conservative vector fields, which kind of leads us to where we're headed here. How do we know if it's conservative or not, right? Okay, so path independence, this is a theorem. And I've already stated this, I've already mentioned this, but check this out. Let's say we're taking a look here at a closed curve. Now this a equals b, this should really be like a equals b, like lowercase. Like the starting point and ending points are the same. So if you start somewhere and wind up at the same point, then that's called a closed curve or a closed path. They have the same initial and terminal point. Then check this out. This theorem says that our line integral is said to be path independent if and only if this line integral over C equals 0 for every closed curve or path in C and D. What? Okay, this is a confusing theorem, all right? Because what it's saying is, I'll do the two-dimensional case. It's saying, all right, we have, let's say in two-dimensional space, we have some vector field in here, okay? There's some vector field in here. You see all the little arrows everywhere? It says that we can say that a line integral, any line integral we choose, is path independent, meaning I can do that one, I can do this one, I can do this one. All of those will give me the same answer, all right? If and only if every single time I do this line integral, I get 0 for every closed curve in here. That means if I could check, if there was a way I could check every single possible closed curve in here, every single one. If every single possible closed curve in this space, if every time I did it I got 0, then I can say that the path doesn't matter anymore. That's like impossible to do. Do y'all understand that? The theorem is nice, but it's impossible for me to actually go and check that every single closed path is 0. That make sense? Okay. So it's a theorem, but it's not as useful as the next one. So how do we determine, first of all, if we have a conservative vector field? So that theorem, I want you to the one I just covered, just kind of know it's there, but don't worry about it. You don't need it. Determining if F is a conservative vector field. So this is the big deal right here, right? If somebody gives us a vector field, how do we know it's conservative? Because if it's conservative, then it's path independent, right? Right? If I have a conservative vector field, it's path independent because the endpoints are the only thing that matters. Okay, so determining if we have a conservative vector field. So first, a picture. This is called a simply connected region, and this is called a not simply connected region. Y'all see the difference between the two? The idea is this. If this region is called simply connected because if I draw any path in here, and imagine shrinking that path down to a point. If I shrink that path down to a point, down to a single point in here, everything gets pushed into a point. As I was shrinking it down, all the paths as I shrunk it were still within the region. Now if I come over to this one, if I draw that path and shrink it down, no problems, right? But what if I draw this path? Now I try and shrink that down, what's going to happen? You have a hole in your region. So you can't shrink that path down past that hole. So this is not simply connected, this is simply connected. We need it for the next theorem. What are the conditions we need for a vector field to be conservative? What are the conditions? So we now establish those.
It has to be a gradient, right, of another function,
Scalar.
or
Well, it's right down there. This is what we have to have. So look at this right here. Let's say we have a vector field, all right? It's a two-dimensional vector field. So we have the first component function and the second component function. So we say, okay, start off with a vector field. Is it conservative? All right, well, as long as this vector field is defined on a simply connected region, in other words, our region doesn't have any weird holes in it, and suppose that both of these, we can take the partial derivatives of them, the first order. So we can take the partial derivative of this, partial derivative of that. If that's all possible, then this is the condition we need to show